Hello everyone, this is Ace My Math and here's my first video. In this channel, I'm going to talk about interesting mathematical problems and give a glimpse into practical mathematical thoughts, which is mainly oriented by middle school students. Today's topic is about an idea combines the composite function and inverse function. Is it possible that there is any relationship between inverse of composite of two functions and composite of the inverse? Will they give the same expression? Well, let's introduce it by taking an example. Here we have two functions, fx equals e to the power of x, and gx equals 2x. So we can easily get the inverse. Then we find the composite, which is fg, and we take its inverse, which gives 1/2 times ln x. Finally, we also take the composite of the two inverse functions, f inverse, g inverse, and it gives ln x over 2. Now we find that they're not the same. Where's the problem? Well, hang on. Why not give it another shot just switching the order? We take g inverse f inverse instead. Look, now we found the same thing. And we can also have gf and we invert it. The similar situation arises. Now we rewrite it like this to make it more clear. Generally, we have discovered that the inverse of the composite of the two functions equals the composite of the inverse, just with a switch of their order. Is it just a coincidence, or it is true for any given functions? Then I took more examples, and finally I found that the equation always works for all the functions I picked. So perhaps it's a fact, but till now, it is still a hypothesis. We should try to give a proof, to prove the equation holds for any functions. But the question is, how? In spite of the equation seems to be a bit clueless and tricky, I think we are supposed to remind of a significant property. Well, did which property of function mention both composite and inverse? Yes, the composite of a function f and its inverse gives x itself. We map x to a function, then we invert it. So they have made no difference. It absolutely returns to x. This property will help us a lot. Let's see. This is what we want to prove. And we just take composite fg to each side. Then the left-hand side can be arranged into a composite of fg and fg inverse. They make no difference, so they can be cancelled out. If you find it a bit hard to understand, you can consider fg as a new function h. So it gives h inverse x. So it equals x. Now our target is to prove the right-hand side of the equation also equals to x. So let's see the right-hand side. After taking fg to the right-hand side, we find g and g inverse are next to each other. See, our old friends show up again. We regard f inverse as a unity and will deal with it later. And now g and g inverse can be cancelled out. Well, f and f inverse remained. And they can be cancelled out again to give an x. See, our proof is done. And it's not that complicated. Now we're confident about that. The property will not break, whatever the two functions are. Okay, but I still wonder if the proof is flawless and rigorous. I must say it does have a little problem, but we can give an explanation about this. We cannot prove an equation by taking an arbitrary function to both sides, when the function is maybe a one-to-many mapping. In this situation, it is okay because both of the two functions are one-to-one, so the composite have to be one-to-one. Now, the deeply hidden and the most interesting part just starts to emerge. Why does the equation break without switching the order? Because when you take fg to both sides, you find that the right-hand side becomes f inverse, g inverse, f, and g. No function will be cancelled out. Actually, I can move the parentheses as I like, but their order cannot be switched during the operation. Mathematically speaking, they do obey the associative law, but they do not obey the commutative law. What's more, the similar situation will arise when it comes to matrix. When we calculate the inverse or transpose of two multiplied matrices, they also switch their order. But this part is actually related to linear algebra, which is highly beyond middle school syllabus, and to be honest, I'm still a green hand about this, so I will not go further for the moment. Alright, that's all for this video. Please like, share, and subscribe if it is roused your interest. And if you have any good or different ideas, please feel free to contact me. Here is Ace My Math. Thanks for watching, and see you next time.